Today, we are going deep, way down inside your computer to uncover the hidden network that makes everything, well, work. I mean, think about it. You plug in a keyboard, a flash drive, a monitor, and it just works. But how? How does the computer instantly know how to talk to it? The answer, it turns out, is a critical component called the bus. To really get why the bus is such a clever solution, we first need to understand the huge problem it was built to solve, connecting a whole bunch of different parts that all need to talk to each other, and fast. Okay, so inside your computer, you've got the motherboard. You can think of it like a sprawling city packed with critical buildings, the CPU, the memory, and all the connection points for everything else. But getting every building in that city to communicate instantly, that is a massive challenge.
And here's where physics comes into play. Modern CPUs run at insane speeds. We're talking 3.8 gigahertz. At that frequency, the electrical signals carrying information actually start to break down and degrade as they travel along the wires on the motherboard. You risk losing information, and that creates a huge design bottleneck.
So, engineers are stuck with this tough choice. Do you run everything at top speed and risk signals getting corrupted? Or do you slow the whole system down to a crawl so the signals are stable? Neither of those is a good option. And this is exactly where the bus system comes in as a really elegant solution. So let's get into it. The best way to think about the bus system isn't as a single road, but more like a complex highway network, a data superhighway built right into your machine. At its simplest, a bus is just a shared pathway for communication, but it's so much more than just a bunch of wires. It's a whole system with rules of the road, a protocol that governs how data traffic flows, making sure nothing crashes. And on this data highway, you've got two main roles. There's a bus master, which is usually the CPU. It's the one that starts and controls the data transfer. It's kind of like the driver who decides where the car is going. And then you have a bus slave, like a memory chip, which just responds to the master's requests. A typical bus has different lanes for different jobs. You've got the address lines, which are like a GPS coordinate telling everyone where the data needs to go. The data lines are like the cargo trucks, carrying the actual information. Then there are control lines, which direct traffic, signaling whether we're reading or writing data. And finally, the clock signal acts like a master traffic light, making sure every single action happens in perfect sync. But here's the real kicker. Modern computers don't just have one bus. No, that would be too simple. To solve that whole speed versus distance problem, they use a whole hierarchy of them. At the very top, you have the system bus. This is the main high-speed freeway connecting the CPU and memory. From there, a thing called a bus bridge acts like a highway interchange, connecting that main freeway to slower auxiliary buses. Think of these as the city streets where your keyboard and hard drives live. And some parts, like a powerful graphics card, get their very own dedicated express lanes straight to the CPU for the best possible performance. And the genius of this tiered structure is that it allows for something called concurrency. What that means is different data transfers can all happen at the exact same time on different buses without getting in each other's way. The CPU can be talking to memory on the freeway while your hard drive is busy doing its thing on a city street. And here's where you see the payoff. Let's say the main system bus handles 200 megabytes per second, an auxiliary bus handles 500, and that dedicated graphics bus handles a full gigabyte per second. Because they can all run at once, your total system bandwidth isn't limited to the fastest one. It's all of them combined, adding up to 1.7 gigabytes per second. Way more than any single bus could ever manage on its own. So we've got this incredibly powerful highway system. But just like any highway, you need rules. And those rules, the protocols, they come with a cost you can't avoid: overhead. Let's take a look at a classic example, the PCI bus. On paper, its raw bandwidth is a pretty impressive 132 megabytes per second. But once you factor in all the protocol overhead, all the time spent managing who gets to use the bus next, the actual speed, the effective data rate, just plummets. It drops to about 19 Mbps, just a seventh of its potential. So how do they fight back against this overhead? With something called block transfers. Basically, instead of sending data in tiny little packets, they send it in big chunks. And you can see how much of a difference it makes. Sending 64 units of data all at once is way more efficient than sending them one by one. That's because the overhead cost, all that setup time, is paid only one time for the whole block. So this brings us to a really crucial point. It's all a trade-off. Sending big blocks of data is super efficient, yeah, but it also hogs the bus, which makes other devices have to wait their turn. This constant tension between efficiency on one hand and responsiveness, or latency, on the other, is one of the biggest challenges in computer design. Okay, so let's bring this all back to something we do every day, plugging new devices into our computers. How does all this connect? When a device, say your keyboard, needs to send something to the CPU, it can't just yell. The system has two main ways of handling this. First, there's polling. This is where the CPU just wastes its time constantly asking every single device, hey, you got anything for me? You? How about you? It's simple, but so inefficient. The much smarter way is using interrupts, where the device basically raises its hand and says, excuse me, I have something, but only when it actually needs attention. But the most efficient method of all is called direct memory access, or DMA. This is a brilliant technique that basically lets a device, like your network card, become its own temporary bus master. It gets to manage its own data transfer directly with the computer's memory, cutting the CPU out of the loop entirely. The whole process is really simple and really powerful. First, the CPU just kicks things off. Second, the device's own controller takes over the bus and does all the heavy lifting itself. Then, finally, when the job is done, it sends just one little interrupt back to the CPU to say, all finished. This right here is why you can stream music perfectly smoothly while your CPU is totally busy running other programs. The computer bus is really a foundational piece of engineering, but it's one that's constantly changing. It started as simple wires and has evolved into this complex concurrent hierarchy, all to meet our never-ending demands for more speed and more connectivity. And as we look to the future, the challenge is really still the same. How do we build even faster, more efficient, and more responsive pathways for the data that truly drives our world?